All right, our first spherical coordinates example starts here with example 3, where we're asked to compute the integral of a function of three variables, x, y, and z, which is equal to x squared plus y squared. Sure, there is no z in this function, but that doesn't mean it is not a function of three variables. It just means that the variable z is unspecified. It's free to be anything it wants to be. And we're going to integrate this function f over the sphere of radius 4 centered at the origin. So what we want to be able to do here is first sketch this region. Not difficult to do so, but it's useful, especially getting started here. So here is a wonky looking sphere. And here are the usual three space axes. Okay. Now what we want to think about here is we're really going to try to be thinking about this definition 1 of a centrally simple region. And this is really saying that spherical coordinates is ideal to use if your region is centrally simple. What's centrally simple? Centrally simple basically means is that if you start at the origin and just draw a ray outward, it doesn't matter what angle or orientation you strike that ray out. Just imagine drawing a bunch of straight lines outward through your region. Now, when you strike such a ray outward through your region, we want to identify surfaces that it intersects with, which is a common feature that we've been doing all along. So in this case, the only surface that it hits is the actual sphere of radius 4 itself. Let's go ahead and label some 4s here to emphasize that it's a sphere of radius 4. So in this case, what this tells us is the outermost surface. So in other words, our rho in spherical coordinates, it's bounded above by 4. Because rho in spherical coordinates, rho is defined to be the distance from the origin to whatever you're talking about. So on a sphere, the rho value is constant. Rho is always equal to 4 on a sphere. In fact, the equation of a sphere of radius 4 centered at the origin in spherical coordinates is simply rho equals 4. But because we're supposed to be integrating over the sphere, the full sphere, we actually are not just integrating over the surface itself, we're integrating everything within. So like the solid sphere, everything. So in this case, you might look at this and say, okay, well, it only hits one surface. It doesn't hit an inner surface. There's no inner and outer surface. There's only an outer. Well, whenever you have a region where you are convinced that there's only an outer, that usually, almost always, I can't even think of an example where this wouldn't be the case, it basically means that your inner surface is just 0 because you started from the origin and your solid region actually contains the origin. So whenever your region contains the origin in spherical coordinates, that means rho is 0. Okay, so we now know the bounds for the rho integral for spherical coordinates. Now we have to think about what is the phi bounds here. Well, since we're integrating over the full sphere, not just the top half or just the bottom half, but the full sphere, think of starting up here at a phi value of 0 and then working your way downward. And as you move downward, what's the lowest you can go? Now remember, in a previous video, we talked about how the maximum range for phi is 0 to pi. It could be smaller than 0 to pi, but the maximum it is 0 to pi. Well, definitely the sphere touches the z-axis, so definitely we're going to start at phi equals 0. But how much do we increase? Well, think about just rotating this. Do you go all the way down to the negative z-axis? Yes. The sphere lives down there as well. So this means for phi, we actually do get the maximum range. And for theta, we want to play a similar game here. Imagine starting off at the positive x-axis and moving counterclockwise towards the y-axis. Now the maximum range for theta is 0 to 2 pi. Does this sphere extend all the way around the z-axis? Yes, we go all the way around. It's not like we only want this half of the sphere, the half of the sphere for which y is greater than or equal to 0. In that case, we'd say theta goes from 0 to pi. Or if we only wanted this half of the sphere, the half for which we have y is less than or equal to 0, then we would say theta goes from pi to 2 pi. But we want the whole sphere. So theta is going to range from 0 to 2 pi. So right here, these three inequalities actually give us our inner, middle, and outer bounds for the triple integral. So we are initially asked to compute the triple integral over S of the function x squared plus y squared over the sphere of radius of 4 dv. Okay. Well, for spherical coordinates, we just determined our bounds. So theta on the outside, phi in the middle, rho on the inside. The next thing we need to do here is actually convert our function into spherical coordinates. That means we need to replace x with rho cosine theta sine phi, and replace y with rho sine theta sine phi, and simplify. So let's do that off to the side here. Actually, we'll do it down here really quickly in red. So x squared is rho squared cosine squared theta sine squared phi. Y squared is rho squared sine squared theta sine squared phi. And that means that x squared plus y squared, well, let's look at what's in common. The sine squared of phi is in common, and so is the rho squared. So let's pull that out. Rho squared sine squared phi. And what are we left over with? Cosine squared theta plus sine squared theta. And what do we know about this? Well, Pythagorean identity, that's equal to 1. So this entire thing just boils down to rho squared sine squared phi. So this integrand, x squared plus y squared, when it's written in spherical coordinates, is rho squared sine squared phi. And now we also need to know what dv is. Well, remember that dv is rho squared sine phi d rho d phi d theta. So we have another rho squared and another sine of phi d rho d phi. Running out of room here, but let's go ahead and see if we can move that around just a little bit. D theta. Now we can integrate this. So let's see if we can buy ourselves a little bit of room here. We should be able to resize this and put that someplace. All right. Moving over here, we can now begin integrating this. So one thing I want to point out to everyone, that when you're doing these spherical coordinate triple integrals, a lot of times there is a symmetry in the functions. Not always, but a lot of times there is. Especially when you are starting with a function x squared plus y squared, there's definitely this xy positive negative symmetry here, the circular symmetry going on. So I wouldn't be surprised if some of these may be 0 or something like that. It's not guaranteed, still have to do them, but be on the lookout for things like that. So notice here that all of our bounds are constant because, well, just like what we learned in Cartesian coordinates, if you have a triple if you have an integral where all of the bounds are constants, you're integrating over a rectangle. Well, here, apparently, this is like a spherical rectangle. In spherical coordinates, all constants produce a sphere. In cylindrical coordinates, all constants produce a cylinder or a portion of a cylinder. Right? If this doesn't have to be 2 pi. This could have been some smaller number than 2 pi, in which case it wouldn't be a full sphere. It would just be a portion of a sphere. Okay. So anyway, to integrate this, because we have all constants in the bounds, and we can actually rewrite this as a function of theta times a function of rho times a function of phi. We can split it up. We can actually split up the entire triple integral. So we can do a theta integral. There's no thetas in the integrand, just our differential. So we have d theta times the integral from 0 to pi of our phis, which should be sine cubed phi d phi. And then we have our rhos, 0 to 4 rho to the 4th d rho. So this integral here is just 1 from 0 to 2 pi. So this whole integral here is just equal to 2 pi. This integral here, this integrates to 1/5 rho to the 5th. So it looks like between the two of them, we get a 1/5 constant from this integral, and we get a 2 pi from this integral. So we should have a 2 pi over 5 integral from 0 to pi. Now this one right here, we can put this one on hold for a second while we deal with the other two. So rho to the 5th between 0 and 4. So this is a constant. This is just 4 to the 5th. So 2 times pi times 4 to the 5th. We'll worry about that in a moment, over 5. Now this integral here, the easiest way to do it would be to take our sine cubed of phi, rewriting it as a sine squared phi times another sine of phi. And then you can go ahead and take this sine squared, write this as a 1 minus cosine squared phi times a sine of phi, and then do a u sub on the cosine of phi. So let's go ahead and do that. So this will be 1 minus the cosine squared of phi times a sine phi d phi. Our u sub here, let's move on over to this side. So u is equal to cosine phi. So du is minus sine phi d phi. U of 0 is cosine of 0, which is 1, and u of pi is negative 1. So our integral looks like it's going from 1 to negative 1. We could swap this to negative 1 to 1 if we take a negative sign. Right here, that's the cost we have to pay for switching them. We can switch them, we just have to pay a price of a negative. But the nice thing is, this negative that we need to pay immediately comes from this negative that we get from our du. So we can basically just cancel these negatives, making them both positive, and then keep our bounds in a nice consistent way. So with that said, this should give us this would give us 2 pi times 4 to the 5th over 5. And this would become the integral from negative 1 to 1, 1 minus u squared du. So this is, let's start rewriting this constant as well. This is 2 pi times 4 to the 5th is 2 squared to the 5th, which is 2 to the 10th. So this is 2 to the 10th all over 5. And then this would be u minus a third u cubed from -1 to 1. And then this right here, I guess we have pi times 2 to the 11th over 5. And then this would become 1 minus a third minus -1. Ooh, this gets a little crazy here. What do we have? -1 cubed is -1. -1 times negative a third is positive a third. So this is plus a third. So it looks like we are going to have 2 to the 11th is, I believe, 2048 times pi over 5. And this would be 1 minus minus, so 1 plus 1 is 2. And then similarly here we have negative a third minus another third, so minus 2/3. And we can factor the 2 out to get 4096 pi over 5 times 1 minus a third, which is 2/3. Which is getting to be a large number, 8,192 pi over 15. And that's the answer.